Hello everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is May 26th, 2022 class videos uploaded. Hello everyone, I have uploaded class videos of May 26th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. The second announcement is the second new announcement is the slides of chapter 2 has been updated, version 2022-0531. Hello everyone, I have uploaded the latest version of slides of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, slides, chapter 2 slides 2022-0531.pdf. Best regards, Wei Zhen. Okay, the third new announcement is the handout of chapter 2 has been updated, version 2022-0531. Hello everyone, I have uploaded the latest version of the handout of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, handouts, chapter 2 handout 2022-0531.pdf. Best regards, Wei Zhen. Excuse me. So next, let us look at the let us look at the progress of the last class. In the last class, we have taught to chapter 2 slides, page 55, okay, which was finished. Okay, so now please open the slides of chapter 2. Okay, and please turn to page 56. Okay, so we are now talking about deep Q learning and resource allocation. For the underlay DSA, okay, here DSA means dynamic spectrum access scheme. The SUs, okay, SU means the secondary user, will perform resource allocation by selecting their target SINRs, gamma I. Okay, SINR means signal to interference plus noise ratio, with the goal of meeting the SINR constraints in equations 2.2 and 2.1. Okay, let us see equation 2.2. Okay, in equation 2.2, it says, similarly, for secondary user I, the corresponding SINR is expected to satisfy the condition gamma I is, okay, it is the SINR for secondary user I is equal to GIS times PI divided by G0S times P0 plus summation I is equal to 1 to capital N GIS times PI plus sigma squared, which is greater than or equal to gamma I, where G0S is the channel gain from the PU, okay, that is primary user, to the secondary base station. Okay, here is the term G0S. And GIS is the channel gain from secondary user I to the secondary base station. Okay, and here is the term GIS. Here is GIS. And gamma I is secondary user I's required SINR threshold determined from quality of service QoS goals. Okay, here is gamma I. Okay, and we have introduced the meaning of quality of service QoS. Okay, if you forget, please look at the handout of chapter 2. Okay, this is equation 2.2. And what is the meaning of Pi, P0 and sigma square? Okay, let us look at the previous slide. Okay, Pi denotes secondary user I's transmit power, where 1 is smaller than or equal to I, and I is smaller than or equal to capital N. P0 denotes the primary user's transmit power, and okay, the transmissions are subject to an additive white Gaussian noise AWGN with power sigma squared. Okay, and what is capital N? Okay, capital N is the number of the secondary users. Excuse me. Okay, let us go back to the slides. Let me see, page 56. Okay, so in equations 2.2 and 2.1, okay, let us see equation 2.1. Then the signal to interference plus noise ratio SINR of the primary user is expected to satisfy the following condition. Gamma 0 P is equal to G0 P times P0 divided by summation I is equal to 1 to capital N GIP times PI plus sigma squared, which is greater than or equal to gamma 0, where G0P is the channel gain from the primary user to the primary base station BS. GIP, okay, here is the channel gain from secondary user I to the primary base station, and gamma 0, okay, here is the PU's, that is primary user's required SINR threshold as determined from the underlay DSA, okay, which is the abbreviation of dynamic spectrum access configuration. Okay, let us go back to page 56. Under the present transmission settings, the selection of beta I. Okay, what is beta I? Okay, beta I appears in equation 2.15 in the previous slide. Okay, so beta IS is the secondary user threshold SINR. So we can see that now we omit the parenthesis S and we have beta I. Okay, the selection of beta I is equivalent to the selection of modulation scheme, channel coding rate, and RIS. Okay, I think you have already known what is modulation. Okay, in the course, if you have taken the course, principles of communications and digital communications. Okay, then what is channel coding rate? Okay, we have introduced what is channel coding rate. I think we should review it again. So please open the handout of chapter 2. Okay, handout of chapter 2. Okay, this. Okay, and search for channel coding rate. Okay, good. Here, channel coding rate. Okay, problem 9. What is channel coding rate? A solution, channel coding rate. Okay, sometimes we use heaven between channel and coding. Sometimes we do not use a heaven here. Okay, so they mean the same thing. Channel coding rate is defined as the number of information bits per coded channel symbol. Okay, so let us go back to the slides. Okay, channel coding rate and RIS. Okay, what is RIS? Okay, let us go back to the previous slide. RIS is the transmit bit rate. Okay, as mentioned earlier, QoE based performance assessment is gaining significant attention as we move toward the 5G era. Consequently, we will now use QoE, okay, where QoE means the quality of experience, as the network performance metric to assess the quality of the delivered traffic. Okay, among the metrics used to model QoE, we chose MOS. Okay, what is MOS? Okay, let us see. Okay, what is MOS? Okay, so on page 51, among these techniques, mean opinion score, MOS, a metric rating from 1 bad to 5 excellent, is the most widely used QoE metric. Okay, so let us go back to page 57, I think. Okay, among the metrics used to model QoE, we chose MOS because of its popularity and widespread use. Thus, resource allocation will be carried on for all types of traffic using a reward function that is based on average QoE. Okay, when we are talking a reward function, okay, you should naturally think about it is related to the reinforcement learning, okay, which is the topic of our a part of topic of this chapter. Okay, chapter 2, reinforcement learning. Okay, for resource allocation in cognitive radio networks. Okay, let us go back to page 57. Okay, since we will concentrate on real-time video, okay, for example, we are using the my cell phone to watch a YouTube video. Okay, this is real-time video. And regular data traffic. Okay, for example, I am checking my email, use my cell phone. Then when downloading the emails, my cell phone will require regular data traffic. We summarize next for this type of traffic how MOS metrics are derived from QoS measurements. Okay, next page. Okay, first let us look at data MOS model from Dobrojevic et al. 2014. Okay, let us see this reference. Okay, let us see Dobrojevic et al. Okay, have wrote a paper, a conference paper, with title Q-point QoE driven path optimization model for multimedia services. Okay, which was published in International Conference on Wired/Wireless Internet Communications, okay, in 2014. Okay, so from Dobrojevic et al. In 2014, the MOSQD for data traffic is calculated as QD is equal to A times log 10 of B times RIS times 1 minus PE to E. Okay, where QD, okay, this one, and PE to E, okay, this one, are the data traffic MOS and end-to-end packet loss probability, respectively. Okay, what is end-to-end packet loss probability? Okay, for example, if I transmit 1,000 packet at the transmitter, and I lost 10 packets at the receiver. Okay, that is, I only receive 990 packets at the receiver. Then the end-to-end packet loss probability is equal to 10 divided by 1000, which is equal to 0.01. Okay, or 10 to the power of -2. Okay, and what is RIS? Okay, let us review it. Okay, RIS is the transmit bit rate. Okay, the parameters A and B are calculated using the maximum and minimum perceived data quality by the end user. Okay, what is the meaning of the word perceived? Let us look at the handout. Excuse me. Okay, let us search for the word perceived. Okay. So page 58, problem 1. What is perceived? Okay, solution. Perceived is the past tense and past participle of perceive. Perceive is to see something or someone, or to notice something that is obvious. Okay, so let us go back to the slides. Okay. Excuse me. Okay, next page. If the transmit rate of a user is RIS and the effective receive rate is also RIS, the packet loss rate is 0. Okay, this is of course correct. For example, if the transmit rate is 1 megabits per second and the effective receive rate is also 1 megabits per second, so this means that no packets loss in the transmission, so the packet loss rate is 0. And the quality perceived by the end user when measured in terms of MOS should be maximum, that is 5. The minimum MOS value of 1 is assigned to the minimum transmission rate. In this chapter, A is equal to 1.3619 and B is equal to 0.6780. Okay, next page. Okay, second, let us look at video MOS model. Okay, the peak signal to noise ratio, PSNR, okay, which is defined as the maximum of the signal power divided by average noise power. Okay, it is a ratio. Is commonly accepted as an objective video quality assessment metric to measure, for example, coding performance. However, it is known that PSNR does not accurately reflect subjective human perception of video quality. Okay, please refer to the reference Shake et al. 2006. Okay, let us look at this reference. Okay, so we can see that Shake, Sabier, and Bovic wrote a paper with title A Statistical Evaluation of Recent Full Reference Image Quality Assessment Algorithms. Okay, which was published in IEEE Transactions on Image Processing in 2006. Okay, let us go back to page 60. A wide variety of techniques have been proposed to estimate user satisfaction for video applications, among which, okay, please refer to the reference Kang et al. In 2007. Okay, let us look at this reference. Okay, so Kang et al. Wrote a paper titled MOS-based multi-user, multi-application cross-layer optimization for mobile multimedia communication, which was published in Advances in Multimedia. Okay, it is a journal paper in 2007. Okay, let us go back to page 60. Okay, among which Kang et al. 2007 proposed a simple linear mapping between PSNR and MOS as shown in figure 2.2. Okay, let us look at figure 2.2. Okay, in figure 2.2, it shows the curve of MOS versus PSNR. Okay, so in the x-axis, it is PSNR from 15 dB to 45 dB. Okay, and in the y-axis, it is MOS from 1 to 5. Okay, we can see that there is a very simple relationship between MOS and PSNR in dB. When PSNR is between 15 to 20 dB, MOS is equal to 1. Okay, when the PSNR is between 20 to about 43 dB, okay, MOS increases as PSNR increases in a linear function. Okay, Then when PSNR is greater than or equal to 43 dB, MOS, okay, it is 25 minutes. Let us take a break.